It's okay?
Yeah, it's okay.
Good morning. I'm Saveria Spiller, and I'm working at the Norwegian University of Science and Technology in Trondheim, Norway. And today I would like to present a pretty new technique to produce metal or ceramic components, which is called Material Extrusion Additive Manufacturing. So I will give a brief overview of the process, and then a description of some of the main process parameters, and finally a comparison with other techniques and some final considerations. So first of all, the technique is a multi-phase process. The main phases are shaping, the binding, and sintering. But before describing the phases, just a quick specification. Material extrusion additive manufacturing has been recently used to print both metals and ceramics parts, or also metal ceramic composites. But I will be focused on metals and in particular on stainless steel. So we can start with the shaping. The shaping is inspired by fused deposition modeling, which is pretty well known and common. Through FDM, the parts are printed layer by layer. They are made of polymers, and the polymer is in the shape of a filament, which is melted and extruded through a nozzle. The innovation with material extrusion additive manufacturing is that the filament of polymer is filled with a high percentage of metal powder or ceramic powder, and that's why it is usually referred to as high-field polymers, HP. Actually, there are three ways to have the material: pellet, filament, or roast, but the filament is the most common shape in which to have the feedstock. Okay, after the shaping, we have the binding and sintering, which are again pretty well-known post-processes common to other techniques such as powder injection molding or binder jetting, additive manufacturing. So basically during the binding, the binder is removed from the part. We can have different types of debinding: solvent debinding, catalytic debinding, or thermal debinding. And after this phase, the part is basically packed metal powder. And then through the sintering, which is a thermal cycle, the powder can start to create necks first and then bondings to densify the part. So it's pretty clear that the process is complicated because there are several phases, and to each phase corresponds several process parameters which should be controlled in order to ensure a good quality outcome. Here I just listed some of the main process parameters, but I also think that it's important to mention that besides shaping, the binding, and sintering, there is another issue, which is the filament fabrication. Actually, there are also metal filament available on the market, but it's pretty common to produce in-house the filament because in this way it's possible to control more parameters and more characteristics which have an impact on all the three subsequent phases of the process. For example, the extrusion quality, the burnout behavior of the part, and the final density. Just to give some examples, here I collected some data from the literature. The mean powder size, for example, affects both the viscosity of the filament, but also the sinterability of the part. Same consideration for the infill content, which average value is 60% volumetric percentage. Because the higher is the infill, the denser would be the part, but at the same time, the filament is stiffner or less flexible. And then the morphology of the powder is also important, and customized powder is in general preferred over water atomized because it's more regular and more spherical, as you can see. And now we can start with some of the shaping parameters that were throughout investigated by researchers because they are also common to FDM process, for example. And we can start with the layout. Here we are speaking about tensile tests, so tensile dog bones, and we can print them vertically on the side or flat on the printing bed. And several researchers were all in good agreement in stating that the vertical layout is in general performing worst at the tensile tests, while side and flat layouts are comparable, even though the side layout, as you can see from the picture, has the additional difficulty that you have to print a support material under the bridge. For example, here we have two fracture surfaces, one belonging to flat specimens and one belonging to a vertical specimens, and the difference is pretty clear. It's interesting because the vertical fracture surface it shows basically a delamination and a detachment of the layers due to poor adhesion in relation with the load direction. Then we also have the layer thickness. We can say that in general, the thinner is the layer, the denser is the part. And to a certain extent, the density is directly correlated to the tensile properties. So the thinner is the layer, the higher are the tensile properties, as you can see from the plot. And other parameters are the infill strategy and the raster angle. There are several types of infill, rectilinear, for example, or honeycomb. But it's also important to choose the raster angle. For example, from the CT scan on your right, we have we see the porosity of 3 different dog bones printed with linear infill, but with 0, 45, and 90 degrees raster angle. And it's pretty clear that the angle affects the distribution of the pores, but also the morphology of them and the size. There will be several other parameters. Just to mention some of them: cooling fan speed, printing speed, flow rate multiplier, the temperatures involved. They affect the surface roughness, the external appearance of the parts, and the adhesion between the layers. And now, quickly, I would like to show the comparison with other techniques, because material extrusion additive manufacturing is usually compared to conventional processes or to SLM, which is another pretty common additive manufacturing for metals. And it's clear from the 2 bar plots that yield strength and UTS of extruded parts are not good enough compared to SLM or conventional parts. But the elongation at break can be comparable and sometimes even higher compared to SLM. This means that probably the parts are more ductile, and this is related to the microstructure. So to finish, the technique has potential to be more cost-effective and faster compared to conventional processes and to other additive manufacturing processes. And being an additive manufacturing, it also has all the advantages related to the concept, such as the freedom of design, the fact that it's mold-free, for example. Plus, it requires simple facilities, and it has mild safety issues and safety concerns. So this means that it can have different application from SLM, for example. But of course, further studies are necessary on the parameters of optimization in order to reduce the defects in the final part and to enhance the mechanical properties of the components. So I hope this was quick and clear.